So, hello everyone. My name is Ábel Sinkovics. I came from the Eötvös Loránd University, Budapest, Hungary. And I'm doing a PhD on the connection between C++ template metaprogramming and functional programming. And today I'm going to present you an approach to make use of the functional programming code or the functional programming paradigm in template metaprogramming. And since we already have the Boost MPL library, I will show you how the Boost MPL library can be extended with tools based on the functional paradigm. And I chose the Haskell as the functional language to base these new things on. So the additions to template metaprogramming and Boost MPL will be following Haskell's logic. And I'm building open source libraries. Yes?
Question, why did you choose Haskell as your
Okay, so the question was why I chose Haskell. And the reason is that there are many familiarities or similarities between the logic of template metaprogramming and the way Haskell programs are constructed and evaluated. Yes? I see. One of the reasons is the laziness. So, the question was why not, why Haskell and why not ML or Scheme or some other functional language? And the answer to that is that the lazy evaluation of Haskell. And many of the features I will show are better suited or seem to be better suited. Are there other questions? Okay. So I'm building libraries for template metaprogramming, and there are a few of them. And I'm going to show you MetaMonad. So everything I'm presenting to you today are implemented in MetaMonad. And you can download it and play with it. Here is the URL. So there is the full documentation as well. And here are the people who are working on these libraries. So it's not just me. And this is the agenda for today. As you can see, here is quite a few features. And I will show you how can these things be provided in C++ template metaprogramming. And as you can see, it's a pretty long list. So I will not be going into the implementation details of these things. I will show you how you can use it and how it works and how you can build things using these elements of MetaMonad. So let's get started. And as the beginning, I will show you the most common example for C++ template metaprogramming, how to calculate factorial at compile time using templates. And here is the template metaprogramming code, and here is the Haskell equivalent. I got this idea from Bartosz Milewski from last year's conference. So there is the Haskell code. And we want to calculate the factorial of n. And we do it by calculating n times factorial of n minus 1. And of course, we need to stop this recursion with factorial 0. And as I said, this is one of the classical examples. It works, and it works fine for calculating factorial or Fibonacci or some other basic arithmetic computations. Yes?
Why are you using enum then?
I just chose enum. I could have used, okay, sorry. The question was, why enum? And the answer is, I could use const int or const expression int. I decided to use enum. There's no real reason.
Okay, it just seems like an unusual representation used for a template. I'm just curious why you chose that.
No real reason. Okay, so this thing works, but if we want to start building more complex things and construct more complex algorithms and execute them at compile time using templates, we suddenly need a large amount of features, such as control structures, algorithms, data structures, lambda expressions, and so on and so forth. And these things are provided by Boost MPL. So doing all these things manually, in a similar way we implemented the factorial would be pretty difficult, but we can just take Boost MPL and use it. And here is a list of features Boost MPL provides. And if you look at it, especially for the first 3 elements, it suggests that Boost MPL is trying to provide a similar environment at compile time that the standard template library provides at runtime. And Boost MPL is a really good library for programmers who try to execute algorithms at compile time but want to think in the same way they are thinking when they are building runtime C++ programs. At the same time, the similarities between template metaprogramming and the functional paradigm are known. So here are a few features that are common in C++ template metaprogramming and what are important when you're doing functional programming. And here is a list of language elements functional languages provide to the developers who are developing code following the functional paradigm. And the idea is that the MetaMonad library provides these language elements for template metaprogramming, the same way Boost MPL provides these things. So using MetaMonad, you can just use querying or algebraic data types or case expressions and so on. And I will show you how you can use these things. So let's start with a pretty simple example. What do you think this is? Well, there was a guess, foobar. But yeah, other tips? Sorry? Who was that? Yeah? Yeah, exactly. It depends. You cannot tell. So if you see this in the middle of a C++ program, all you see that is it's a template class inheriting from something else. But if you put a comment there saying, well, this is a template meta function and this is template meta function forwarding, that helps the reader a bit. And MetaMonad provides a macro where you can say that, okay, I want to define a template meta function. It's called foo. It has 2 arguments, a, b, and this is the body. And it will generate something like this. And now this macro is just a pretty printing thing, or at least a syntactic sugar. Later on, it will provide something more. Another example, and this is very important for all of the features that we have. Here is an expression, a template metaprogramming expression using Boost MPL. It says if true, then 2, otherwise 7. What do you think the result of this will be? Sorry? Yes. So it will be MPL int 2. So let's make it a bit more complicated. Let's say 1 times if true, then 2, otherwise 7. What do you think the result of this will be? Yes? Yes, so the guess was that it will not work, and this was correct. One may think that the result of this is also 2, but in the reality, it produces a pretty ugly compilation error. I will show you right now. I haven't said that. I just said it will not work. So this is the problem. If you look at this expression, if true, then 2, otherwise 7, then it's an instance of the if template class. And when you call the times meta function with 1 and this if thing, then this if thing is passed to times as it is. And times, so this error message is a pretty ugly way of saying that times has no idea how to multiply an int with an if, because this if is not evaluated. This is kept as if. And that is the problem. And yeah?
Are you going to make a macro that will evaluate the if?
The question was if I'm going to make a macro that will evaluate if, and my answer is no. But I will do something else that will evaluate if. So if I access : type of this thing, then it will evaluate to 2, and then times will be called with 1 and 2 as arguments, and the result will be 2. And this thing is a calculation that has all the arguments that it needs, but it's not evaluated yet. It can be passed around across function calls and be evaluated at a later point in time. And in many functional languages, this thing is called a thunk. And what we can do is write something that will evaluate if, and this something will be a helper meta function called lazy times. It takes the same arguments as the original times, but the idea is that this lazy times will access that : type thing, and then call the original times function. So the user of this lazy times, us, we don't have to worry about putting : type there, because lazy times will take care of this. And meta functions that access : type of their arguments are called lazy template meta functions. And lazy times is called lazy times because it creates a lazy version of times. So it's a lazy wrapper of the times meta function. And there is a problem there. It will access : type of everything, not just this thunk, but also this int1. And to make this thing work, int1 has to provide this. So if you access : type of int1, it has to give int1 back again. And then when you use it in lazy meta functions, it works fine because a : type will be int1 again, so it will not break things. And metamonad calls these things template metaprogramming values. So a template metaprogramming value is something that has : type, and it points to the same type again. And the constant wrappers in Boost MPL provide this. The constant wrappers in the standard library of C++11 provide this as well. So they are template metaprogramming values. And metamonad makes an assumption that every class we use in template metaprograms as values are template metaprogramming values. So they have a : type pointing to themselves, like this. And this is important, obviously, because we can safely call : type every time on every value, and we can just say : type, : type, : type. Yes?
Well, what about like a lazy value or something like that?
What do you mean?
Type on it twice in order to get the true value of the computation.
Okay, so the question was, what about a lazy value that you have to call : type twice to get the value? And my answer is that metamonad makes another assumption that's not on the slide, that when you evaluate a meta function, you get back a template metaprogramming value.
So you never get back a lazy value?
Exactly.
Okay, so all functions always return template.
Yes, so every function returns a template metaprogramming value and not a lazy value. Yes. It causes a problem, actually, this assumption. What about int? What if I want to create a type list with an int in it, or do some compile time calculations with the built-in types that are obviously not template metaprogramming values? So this would break. And the idea is that it's pretty easy to write a boxing class for these things, such as int, and then pass box int around in template metaprograms. And at the end, we can, of course, unbox it easily once we're done with the computations. Okay, so we've seen what laziness means and why it's important. let's look at factorial implementation, and let's look at how the factorial can be implemented using Boost MPL. Here is the template metaprogramming code, and here is a runtime C++ code this time. And the factorial of n is if n is 0, then 1. Otherwise, it's n times factorial of n minus 1. And because the meta functions in Boost MPL are not lazy, we have to put colon types everywhere to make it work. And let's look at it, what happens if I try to evaluate the factorial of 0 using this. Of course, the body will be instantiated with 0. And everything that has colon type on it will be evaluated, which means this will be evaluated to true, this will be evaluated to -1, and this will also be evaluated, which means that we will evaluate the factorial of -1. And the problem is that because we had to write colon type everywhere, this thing was evaluated before eval-if could choose between the two cases. So it's something like eval-if now evaluates both cases and then chooses one of the results. And because of this, the recursion never stops. So laziness is not just a simple syntactic thing that we have to put colon type there or not. It also makes the implementation of recursive meta functions difficult. Yes?
So in other words, in trying to make the evaluation lazy, you actually produce eager evaluation.
I'm sorry? What I'm trying to introduce?
Make the evaluation lazy, you actually produce eager evaluation. So that evaluation is what the problem is eager in the sense that it's not waiting for the execution of the array expressions.
What expression? I'm not sure I'm getting it.
Okay. So you said that this expression is being evaluated before we have enough information about
This.
about all the elements that the values to be evaluated. Okay. So that makes it eager, right?
Yeah. Well, what makes it eager is that both sides are evaluated before the condition could choose. If that's what you mean.
Yeah, that's what I mean. So I was trying to restate what you just said. So by trying to make the evaluation of eval-if, the big expression of trying to make it lazy, you actually produce expressions that are being evaluated eagerly.
I haven't tried to make it lazy yet.
Oh.
I tried to look at what Boost MPL provides now.
Yeah, but you added the colon types everywhere.
Yes. And that's eager evaluation. Lazy evaluation is adding a lazy wrapper to every meta function.
Yeah, you can in a journey from non-lazy to lazy and you're at an intermediate state, so I think later go on, I think something that makes more sense.
I'm sorry, I thought that when you were adding the colon types, that was
That's forces reasoning.
okay.
That is eager evaluation. Okay. So if we do the same thing with lazy meta functions, so this code is the exact same as we had before, but this time instead of using the eager meta functions directly from Boost MPL, we use the lazy versions of these things everywhere. And now, if I try to evaluate the factorial of 0, this thing gets instantiated, so this body is instantiated, but we have only one colon type in it, which means that only this thing will be evaluated eagerly, and the rest of the evaluation happens in a lazy way. Which means this is the definition of the lazy wrapper of eval-if, and it evaluates the condition, which is true, and then it calls the eager version of eval-if with the two possible options. And now eval-if can say, okay, and I choose 1, and that's it. And it will not evaluate the other case. Yes?
Now, semantically, if you look at a meta function that takes in
So you're asking if I used here a lambda expression.
So yeah, instead of having a lazy if, take each of those expressions and make them into lambda expressions that take 0 arguments. Is that semantically equivalent to just removing the type and using your lazy if?
So the question was, if I use a lambda expression with 0 arguments, is the same as I'm doing here with laziness. And my answer is that it depends on the body of the lambda. So if you look at this code, the problem here is that I had to use colon type everywhere, at every level. And if I replace this thing with a lambda, then the body will still need colon type everywhere. Because times doesn't accept trunks. It needs them to be evaluated. And I would have the same problem because of those colon types. Are there other questions? Okay. So we've seen how important laziness is for implementing recursive template meta functions. And now comes the price of using laziness. And I demonstrate it by showing you what happens if I evaluate the Fibonacci of 3 in a lazy and in an eager way. In an eager way, it can be implemented using a helper meta function, which I haven't showed you, but it can be done. In a lazy case, Fibonacci 3 will instantiate Fibonacci 3 minus 1 and 3 minus 2. Fibonacci 3 minus 1 will instantiate 3 minus 1 minus 1 and 3 minus 1 minus 2, which means that there are 5 instantiations of Fib. In the eager case, the argument of Fibonacci has to be evaluated before we instantiate Fibonacci. So Fibonacci 3 instantiates Fibonacci 2 and Fibonacci 1. And Fibonacci 2 instantiates Fibonacci 1 and Fibonacci 0. But memoization comes into the picture, and this becomes 1 template instance instead of 2. So in this case, in the eager case, we instantiated only 4 factorials, or Fibonaccis. And this seems to be a small difference for Fibonacci 3. But using Zoltán Porkolabs and Zoltán Boroknagy's template metaprogram debugger, which they will present on Thursday, I have generated the same diagram for the Fibonacci of 10. And as you can see, there is a huge difference in this case. And I have created the diagram using the same tool, counting the number of instantiations, using or calculating Fibonacci in a strict way and in a lazy way. And it's linear, so it's 500,000 of 1 million and so forth and so on. It did, it all compiled, and this was the number of template instantiations.
You have to give the compiler like gives you 10 kilobytes of RAM?
It uses a lot of memory. So the major problem with template instantiations is that the memory consumption will be extremely high. So the question was that did I tell the compiler to use 10 gigabytes of memory? And when the memory consumption gets extremely high because of the large number of template instantiations, then it seemed to slow down the compilation in a very bad way. So when the compiler has to start swapping and these sorts of things. But I didn't give Clang any extra options. I was using Clang because the debugger uses that. Okay. So we need laziness, but we have to be careful with this because of this price. And let's start to look at the different features I have listed so far. So now we have laziness. We have seen how laziness works. And now let's start using it. And here is an expression, 11 plus 2. It's a template metaprogramming expression. It uses Boost MPL+. And if I use : type on it, it will get evaluated, and I get 13. And the idea is that why would I evaluate it? I could pass this expression as an expression around in template meta programs, and the expression itself would be the value. And I could call meta functions and pass this expression as a value to them, and meta functions could return this expression as a value to me. And by expression, I mean the syntactic form of an expression. So you can think of it as an AST, plus, 11, and 2. And I don't really care about what it means, how it would be evaluated. It's just an expression. And if I introduce a wrapper, let's call it syntax, then I can protect it from being evaluated. And I can keep it as an expression. So if I call : type on this syntax, I will get this syntax back. And I can call : type on it as much as I want. So I can call meta functions and give them this syntax, which means I give you this expression 11 plus 2, and they can return this expression 11 plus 2. Yes? Yeah, so the question was that is syntax exactly like box? And yes, so far it's exactly like box. But there is an extra thing to it, eval syntax. So when I say that, okay, I've been passing it around as a value, and now I want to evaluate it, then I get a meta function, eval syntax, which unwraps it and then evaluates it, which means that it will give me 13 back. So it says, okay, now the time has come, let's evaluate this thing now. And then I get 13. And this is not something you would do for box. This thing becomes interesting when we introduce variables. Let's say a variable is an instance of the var template. And every variable has an identifier, which is just a type. So if I want to create a variable a, then I can declare this a type and then refer to this variable as var a. And then I've got an expression with an open variable in it. And I can create a type def to make it look better. So I can say that type def var a, and after that I can refer to this variable as a, which makes it more readable. And of course I could do the same for b, c, d, and z. And MetaMonad provides a header file which defines all these one-letter long variable names. But if you need other variable names, you can just create your own this way. What happens if I try to evaluate this thing? So the question was that I have no binding for A. And yes, I have no binding for A. Yes, that is an error. If I try to evaluate it, it will try to evaluate 11 plus A. And plus will complain that it cannot deal with a variable. So let's do variable binding, or it is actually a variable substitution. So it says, take this syntax and replace every occurrence of A with this other syntax. And this is just a syntactical transformation. So this thing doesn't really care about the semantic. It just takes this expression, searches every occurrence of A, and puts this other expression there. Yes?
And what if there's like another syntax within your syntax that you say? You're going to substitute that one too?
So the question was, what if there is a syntax inside a syntax? And as Dave said, syntaxes are similar to boxing, so they protect their content. It will stop at the inner syntax. So it will not go into the inner syntax or into a box. These things protect their content because they may be something you don't want to or you should not touch. Okay. I called it let because it is extremely similar to the let expressions of many languages, including Haskell. And when I evaluate this thing, I will get another syntax back. So it's just a pure syntax transformation utility. It will not evaluate it. It will give 11 plus 2 back. And in Boost MPL, there is a convention that if I have a meta function taking a boxed value, then there is an underscore C version of it, which takes the unboxed version of the value. And following a similar logic, MetaMonad introduces the underscore C version of let and many other utilities that operate on syntaxes. And let C wraps this thing and this thing with syntax and calls the original let. But it makes the code look simpler. Was there a question? Or? Okay. And using this makes the code look better, and it's easier to read the code. If I want to evaluate the resulting syntax, then I have to wrap the whole thing with eval syntax. So it will do the substitution, and then eval syntax will do the calculation, and this will give us 13 back. And because this is often needed, MetaMonad provides an eval let C, which does let and eval syntax together, which makes the code, again, more compact. Another thing we can do with these syntaxes is something I'm going to show you now. Here is an example syntax, A plus B. And this syntax could be the body of a lambda expression. And the arguments of that lambda are the variables A and B. And this thing defines a lambda expression. So it's basically a template meta function class. And we can give it a name, such as add. And then we can use it as any other template meta function class. So we can call it with 11 and 2 as arguments. And then we get 13. There is, of course, an underscore C version of this as well, which makes it easier to use. What do you think happens if I call it with one argument only? So I call it with 1, and that's it. Exactly, currying. So it will be another lambda expression, which takes the other argument only, and substitutes A with 1. Well, actually, the implementation of lambda does the substitution using let, and the evaluation of the resulting expression using eval syntax. So everything is built on top of let and each other. I can give this new lambda expression a name, such as inc, since it increments its argument by 1. And then I can just use it as any other lambda expression. So I can call it with 12, and then I will get 13 again. And another thing MetaMonad provides, so if I use this meta function macro to define a meta function that adds 2 values, and I call this meta function with 1 argument, it will also do currying for me. And it will also define the same lambda expression, so I can call that thing inc as well. So that's another thing this meta function macro gives us, currying for simple meta functions. Another thing that is a big problem in template metaprogramming, how do we handle and report errors? And here is an example expression, divides 1, 0. So I try to divide 1 by 0. What will happen if I try to evaluate this? Sorry? Yes, boom. So it will try to evaluate this expression, and it will give us a compilation error. So let's create a safe version of the division, which will give us some extra or special value when the division cannot be done. And if there is this boom thing, then there's no way to recover. So I cannot write a wrapper code on top of this that recovers from that error situation or provides a meaningful error message or a nicer error message. But if I provide a save divides function, which returns some special value in case there is, or in case the division cannot be done, then I can wrap this function call with some other code that provides a more meaningful error message or does something else. And it can, of course, be implemented that way that I say if b is 0, then return a special value called nothing. Otherwise, do the division and wrap the result with just. So these save divides will either give me nothing or just and the result back. And these names came from Haskell, where there is a type called maybe. And the values of that type are either nothing or things wrapped by just. And this is used exactly for this, for reporting errors. So if the compilation went fine, I return just and the result. Otherwise, I return nothing. I mean the volume, nothing. Yes?
Would you consider using like the boost equivalent namage, like calling it optional and none?
So the question was if I considered using the boost names optional and none. And I was trying to follow the Haskell naming convention, and that's why I used nothing and just. So that's why it's called nothing and just. Okay. In Haskell, these two things are called constructors because they are used to construct values. So when I return nothing, then this is a value in metaprogramming. So it has to be a template metaprogramming value, of course. If I return just 13, for example, then that is a value again. So it has to be a template metaprogramming value again. And there are other tricks in the implementation of these things, which one should be careful with. And to make it more simple, MetaMonad provides a macro where you can say that, okay, I want a maybe type with two constructors, nothing taking no arguments, and just taking one argument. And this thing will generate everything for you. And even querying for constructors with multiple arguments. Yes?
Are you using C++ 11 features?
No, it's all C++ 98.
You could get rid of a lot of parentheses, I think.
I know, with variadic macros. Yes? It uses the preprocessor. So how this thing is implemented, it uses the preprocessor library of Boost.
Yeah, but how does it, so what does that kind of thing correspond to the, or is it in C++ without using that?
So that thing will generate these types with their full definition.
Oh, so you just generated normal definitions.
And the definitions as well. So it generates the declarations and the definitions. With all the tricks you have to be careful with.
But then where does reader come into it? Can you just ask me? So you have MPL with data maybe, colon, nothing and just. I'm trying to understand where does maybe go?
Well, maybe goes into the definition of nothing and just. Unfortunately, in C++ template metaprogramming, you cannot express that nothing and just build up a type. They are just independent constructors. And MetaMonad provides a meta function you can use to query this maybe thing from nothing and from just values, but that's all it is there for. So it's more information to the reader of the code rather than the compiler. That you just give it a name. Because it makes it easier to read the code. So that's why there is that name.
So maybe isn't used anywhere? I mean, maybe is just ignored in that macro.
The question was, is maybe just ignored in that macro? And almost. It is almost ignored. As I said, there are meta functions that you can use to query this maybe from nothing. So you can use any value, be it using these constructors or constructors of any data type. And you can say that, okay, and give me the name of that type. And it will give maybe back. Yes?
So you basically use that to both generate declarations for these data types, the data types calculate just
Yes. So it is for the generation of these constructors and for documentation as well. Yes?
And what about like a deconstructor? Do you have something like that?
What
Like,
do you
like
think
the
of?
lowercase maybe function in Haskell?
I don't know that.
So a constructor, you have these two different things, and they each have their own arguments, right?
Oh,
So a deconstructor will
so
take
okay.
in a function that will handle each of those key scenarios.
So the question was, what about a deconstructor? And there is no such thing. There is pattern matching. That will come later. Are there other questions? Okay. When I use this just 13, then I want it to be a template metaprogramming value, which means if I put : type on it, then it should give just 13 back. But this just thing is more complicated than that, because in this case, for example, I'm using it as a lazy template meta function. I call it with this tunc, lazy divides and two numbers, and when I call : type on it, I want to get this just back. I want to get just 13 back. Yes? Save divides is the name of this template meta function. So just has to be a template metaprogramming value and a lazy template meta function at the same time. And it works that way that when you have just t with some type t, and you use : type on it, it will instantiate just with t : type. And if there is a value inside that, then it will remain the same. So it will instantiate itself again. And when there is a tunc in it, it will evaluate that tunc and then give the result back. And this is all done for you by MPL data. Okay, we've got this save divides function, so let's use it somewhere. Here is a meta function, which is more of a demonstration than a useful example. There is a div or first meta function taking two arguments. And it says that when you try to do a valid division, such as 6 divided by 2, then it will give the result back. But when you try to do an invalid division, such as 1 per 0, then it will give the first argument, that a, back. And how can we implement it? Using this save divides function we just created. Well, we can check if save divides could do the division or not. When it could not do the division, then it returned nothing. And if it returned nothing, then we should give a back. And the question is, what should we give back when the division could be done? The problem there is that when I call save divides with some valid values, then I will get just 3 back. But I should give 3 back and not just 3 back. So I should unwrap it somehow. And the way functional languages approach it, or most functional languages approach it, is pattern matching. So you say that here is this expression save divides, which will give me something like that back. And if it's a just n, then let's give n back. If it's a nothing, then let's give a back. And MetaMonad provides a construct that can be used to do this thing. So you can say that eval case, and here is the expression that you want to evaluate. And then you can say that here is a pattern. If the result matches this pattern, then give n back. If the result matches this pattern, let's give a back. The syntax is similar to Eric's syntax, but case and match are in a reverse order.
So with this, is there any kind of type checking going on here?
No type checking. There's
Does it look
Yes, so it could look at that just and nothing are both maybes, but there is no type information. Well, the information is there, but it does not check it. So it say that you can match anything. Yes?
About the type checking question, basically, when I first presented the MPL at ACCU, Stephen Jones was there, and he pointed out that unlike metaprogramming in Haskell, it is essentially dynamic, a dynamic language that compile time. So what we're doing with MPL is we make everything into one-time thing, a type, and there is no type checking. You really take away all of the type checking, that's a very naive and effective approach for getting stuff to compute. But it would be interesting to think about bringing type checking back, especially now that we have C++ 11. There's a lot you could do that would be a lot less inconvenient than would have been in C++ 3. 60% of, say, integers on types.
I'm not going to repeat that. Are there other questions? Oh, yes?
So Divo first essentially refers from either A or B.
Divo first returns either A or A per B.
Yeah, so okay, so I guess I'm just curious as to see if at some point we're going to somehow redefine that in terms of a special type that we call either, the same way that we have AD earlier.
So the question was if there could be an either type, and yes, there is an either type. It's also in MetaMonad. I use maybe instead because it's simpler to show.
Well, but the return value of that expression is basically either A or B, right? Because all of the type B and
Okay. There was a question there.
Maybe I missed where did you get the n variable? It's from the evil case. It's from
Okay, so the question was what that n variable is, and here is the answer. So the way pattern matching happens, well, n variable itself.
how do I know it's named n?
Okay, so n variable is constructed the way I showed it earlier, that var n underscore, and that says this is a variable. It's just a type def of var n underscore. So it's pretty easy to say that this is a variable because it's an instance of var. There is a type def on it to make it look better, but it's just an instance of the var template.
Where did I get the name n? Why it's not x or y or z?
It was my choice that it's n.
So
That's
it's
why.
not something in the evil case.
No, no. It has nothing to do with the evil case. It has to do with the pattern, and this is why.
It's just an example.
It's an example, exactly. And so a pattern is just an expression as well. It's a syntax, and it says it's just with the variable as its argument. And pattern matching happens in a way that this value coming from save divides is also an instance of this just template. And pattern matching says that, okay, they are instances of the same template, so let's compare the arguments. And there is a variable in the pattern, and then it says, okay, this binds the value 3 to the variable n. So using n in the pattern specifies the binding of n. And then I can use this n in the body of that case and refer back to this value. That's the way it works. So the pattern defines what the variable refers to, and then in the body I can use the variable and the value referred to by the variable. Okay. And as I said, these things are all just syntaxes. So there is the non_c version of this thing. And as you can see that there is an evil case meta function, which means that case will just choose one of these bodies, do the substitution of the variables, and give that syntax back. And you need to use eval syntax on it. Yes?
So are you limited to only 2 cases?
Sorry?
Are you limited to only 2 cases?
The question is if it's limited to 2 cases, and the answer is not. But so MetaMonad at the moment uses only the old standard, which means that these things are generated using preprocessor macros. So there is a limit on the number of cases, but it's configurable. Are there other questions? Okay. Let's look at a simple meta function, less. It's a meta function we're writing, so it's not the less of Boost MPL. We want this less to work in a way that if I try to get or compare 2 numbers, I can do it. If I want to compare 2 lists, I can do it, and it will do a lexicographical comparison. So I can compare lists and numbers using less. This can be implemented in a similar way. Less is implemented in Boost MPL using tag dispatching. Its implementation is not important at the moment. We just assume that it works this way. What happens if I try to compare things that cannot be compared, such as an int and a double? What should happen? Sorry? Yeah, so a type error. I get some sort of a type error. Well, that's good, but that's, again, not recoverable. So if it's coming from a library, then so it's coming from the bottom of the library, then it will show the internals of the library in the error message. I don't know what that means.
Would you return like nothing?
Return nothing. Yes, I could return nothing, and that's a good question. But I will not return nothing. I will rather create a new data type, exception, taking exactly 1 argument. And that 1 argument will describe the error itself. And then I can return exception, values cannot be compared. And of course, I can create a struct called values cannot be compared. And that struct will represent the error message. So if anyone calls less with invalid arguments, he will get back an exception value.
Can you catch these?
Well, it will come. So catching these will come. We've got a comparison function that can return exceptions. So let's implement a minimum function using this. This is a minimum function calculating the minimum of A and B. Well, this is how you would implement a minimum. If A is less than B, then return A, otherwise B. So it's a pretty straightforward way of writing the minimum function. If I try to use it to get the minimum of 2 numbers, it will, of course, work. If I try to get the minimum of 2 lists, it will work. What happens if I try to get the minimum of 2 boxed values? One guess is exception. Well, it will give this error message. And the problem behind it is that the result of less will be an exception for you. But if we'll not be able to deal with an exception as the condition. So if we'll complain that I want a true or a false here, and I cannot do anything with an exception there. So we should do something else. We should avoid giving if an exception value. If less returns an exception, we should propagate it further without calling if. And one way of doing it is using an evil case. So let's take this part, this sub-expression that may return an exception out of this, and create a pattern that is a variable itself, so it matches everything. It will match the result of less, and I can use it as the argument of if. And then if less return the real value, then I can call the if code and do the processing. And I can also create another pattern which is an exception. So if less returned an exception, let's just return that exception to the caller of min. Yes?
Why couldn't it just, if any of its arguments that it pulls in lazily throws an exception, then it just passes it on over?
So the question was, why couldn't if deal with this exception as argument? So if anything is an exception, let's just forward it.
Not anything, anything that you value.
Yes. So if could do that, but I will show you how you can prepare these things for propagating exceptions. So if cannot do it at the moment with Boost MPL, and we can implement exception propagation without changing if. And I will show you how. Yes? Okay. So now we've got this code and it does the propagation. So if I try to call minimum with two values that cannot be compared, it will return that exception to me. And it does this thing, but the problem here is that the exception propagation and the business logic, which is calculating the minimum of two values, are mixed together here. So let's try to separate these two things, calculating the minimum and propagating exceptions. And the way it can be done is that, first of all, that we needed less here is not that important. It could be an argument. So it is just an arbitrary expression there. And the same holds for the code that says what to do with the result if there was no exception, how to go, what is the continuation. So in this case, if that thing was true, then return A, otherwise return B. It is also just some code to do. So I can make it an argument as well. And then I get a function called bind exception, taking a value and code what to do with it afterwards as arguments. And it can say that, okay, if that value was an exception, then let's just return that value. Otherwise, call that what to do with it afterwards with the value, which is guaranteed that it's not an exception. And using that, I can implement minimum. So I can say that, okay, bind exception, the first thing to check is less AB, and if it was not an exception, then let's just use if and return A or B. And of course, I can use bind exception to do something completely different, such as summarizing three values. And I can say that, okay, let's add A and B together. And if it was not an exception, let's add C to this. So I can reuse this bind exception. And these functions don't have the exception propagation logic in them. But of course, it is not that convenient to use it. So it makes it really difficult to read the code. And these things were simple. So here is a more complicated example, getting the minimum of three values. And this gets this complicated using this bind exception. So it's not that useful in this form. But what if I could do this? So implement minimum of three values in a way that I say, okay, let's use the L variable and store a Boolean in it if A is less than B. And then let's store the result of this if in M. So if A is less than B, then M will be A. Otherwise, M will be B. So basically, M will be the minimum of A and B. And then I can compare this M to C. And then I can say that, okay, and let's return M or C, depending on which one was smaller. And
So this is kind of like C, right?
yes. So it's a sequential code, basically. And you can use variables in it. And MetaMonad provides this thing. You can use the do template, and then you can write this code and do the computation in small pieces, but at least in a more readable way than before. And in the background, this do template will call bind exception and combine bind exceptions together. Okay, let's make it a bit more simple. So the minimum of A and B looks like this. And this is more readable than using bind exception directly, but this is not that ideal. So this is the way we want to write the minimum calculation if A is less than B, then A, otherwise B. And MetaMonad provides a template called try, which takes this expression as a syntax and generates that thing out of it. And then I can use a complex expression here, combine things in a way I want, and this try template will generate that thing for me and do the exception propagation automatically. Okay, let's make this minimum function a bit more complicated. So when I try to compare things that cannot be compared, I don't want it to return an exception. I want it to return the first argument, just to follow the earlier logic. And well, the name try suggests that there will be a catch as well. I can say that, okay, if this thing threw an exception, and this exception was that values cannot be compared, then return A. So you can catch these exceptions as well. And of course, you can have multiple catch cases. So you can say that if there was any other exception, then let's just return B. And of course, you can have multiple catch cases, and they are checked in order. And this thing is just a syntax. It's a predicate deciding if you want to catch the exception. And this is the body, which is also a syntax. So you can see the underscore C's everywhere. Okay, so we could do cool things. Let's look at that, how we could generalize this thing. We had this bind exception meta function, and we built a do thing on top of that provided a better syntax for using this bind exception. And we put a try template on top of that provided an even better syntax for this thing. And what if I would use a bind for some other type? So what if I would have a bind maybe, which does something similar for nothing and just things? And I could build a do template on top of that. And I could have a bind list doing some magic with lists, and I could put a do type of thing on top of that. And how can I do that in a way that it makes sense? Here is the original version of minimum function using bind exception directly. And if I look at this bind exception, what it does is that it takes something that's either an exception or a value, and then it takes a function telling us what to do with that value if it's not an exception, and it gives us another exception or a value back. And that function took a value. So that function could assume that this thing was not an exception, and then it could produce either an exception or a value. And I could generalize this idea. I can say that, okay, bind functions should work in a way that this thing is some set of values. In this case, it's either an exception or a value, and then there is a function taking a value and providing an element of this thing, and then bind could provide an element of that thing at the end as well. This set of values is really just a set of values in template metaprogramming. In Haskell, it is defined by the type system, but we know that there is no type system in template metaprogramming at the moment. So one bind operation is this exception or value thing, but here is another example. We could say that, okay, this set of values could be values of that maybe type we had earlier. So this can be either a nothing or a just value. And I could define a bind operation for that as well. And it can be defined that way, that if it was nothing, then don't call the function. If it was just something, then call the function with that something. Now, this set of values was easy to use in this case, because here everything belongs to that set of values. So everything is either an exception or a value. But in this case, elements of this set have to be either nothing or just things. And I need a function that takes an arbitrary value and produces an element of this set out of that. And after that, I can easily use this bind operation. And in the maybe case, it can just wrap the argument with just. In the exception case, it can just return the value unchanged because it's already an exception or a value. And by using the combination of this bind and return thing, the do template I showed you earlier can be used to combine different steps together, either using this bind exception or this bind maybe. And it can provide a better syntax for writing complex use of this bind operation. And if I use this bind operation, then I don't have to unwrap every just thing here, and I don't have to check for exceptions here. So these small functions can implement the business logic, and the bind exception or bind maybe will implement the error propagation logic. What about lists? What if I wanted to define a bind and a return for lists? How could this work? Well, the set of values are the list values, or the lists. I can define this return operation in a way that if you give it a value, it will be the one element list out of it. And I can define a bind operation that takes a list and some function and produce another list. And that function takes a value and produces a list out of it. And to understand the way bind works, let's look at a simple example. Here is a simple example f function. If I call f with 1 as argument, it will produce this 2-element list. If I call it with 2 as argument, it will produce that 1-element list. If I call it with 3 as an argument, it will produce that other 1-element list. So for every argument, it will produce some list. And I can build a list of these values. And I can call bind and say that, okay, this is the original list, and use this f function we have just defined as the operation. And what this bind operation can do is that it can call f for every argument or every element of the list, and then produce a list of lists. And it can, after that, just join these lists and produce the final result, which has to be a list. So this way, we have managed to create some sort of a bind operation that satisfies all the rules I have just shown. But the question is, why did we do it? So, okay, we're good. We made it. We've got a bind operation for the lists. But what can it give us? And one thing it can give us, and I will show you, is list comprehension. So in many functional languages, there is an option called list comprehension, or there is a possibility called list comprehension, which we can use to implement list operations or operations on one or multiple lists in a really compact and easy to read way. And using this do thing I have shown you, and it comes from Haskell, of course, and this bind operation and return operation for lists I have shown you, this list comprehension can be implemented, which means that since we have that do template in template metaprogramming, and we have the bind operation for lists, we get this list comprehension in template metaprogramming out of the box. And I will show you how it works. Yes? Yes. This is the example. So the example I will use to show how it works is solving this problem, which is give me all relative primes from 1 to 100. And here is Haskell code using list comprehension, and here is C++ template metaprogramming code using this bind list and do operations. And the result of this thing will be, of course, a list, and a list of pairs, number pairs, that are relative primes. So in Haskell, I say, okay, I and j pairs are the results, and I say the same in template metaprogramming. Return ij pairs. And I say that, okay, I ranges over the 1 to 100 list, and I can use it this way in template metaprogramming. And I can say that, okay, j is the same. It ranges over 1 to 100. And I can say that, okay, but I want to keep only the relative primes. So I want to keep only those pairs where I and ji are relative primes. And of course, I assume that the function deciding if two numbers are relative primes is available. And if it is available, then that's it. I have implemented the code getting all the relative primes from 1 to 100. And another way of thinking of this is this pseudocode. So it works as if I wrote this. A loop goes from 1 to 100. There is a nested loop going from 1 to 100 again. And if these things are relative primes, then keep that pair. And that's it. This is how it works. Yes? Guard is a function that either returns a one-element list or an empty list. And this is because it works in a way that when you say set I and you provide a list here, then it will take the remaining of these two blocks and evaluate it for every I in that list. So every I from 1 to 100. And the same happens here. And if I don't leave it there, then this return will be evaluated to every ij pair between 1 to 100, following this logic. But if I have this thing here, then if the expression is true, then guard returns a one-element list, and this thing will be evaluated once because of that one element. It can be anything. But if this thing returns an empty list, then this thing will be not evaluated because it will be evaluated 0 times. That's how it implements this condition. Yes? Okay. So the question was why returns a list and not just a Boolean or maybe. And the answer is that everything here has to return a list because this is a do block on lists. Because if there was a Boolean or a maybe or something, then the bind operation for lists couldn't work because it expects a list. And a do block for lists uses that bind operation for lists.
So is that do block similar to do notation?
It's exactly, yeah. It is the do notation of Haskell in template metaprogramming. Are there other questions? I've shown you bind operation for maybe, exceptions, and lists. But here is a list of other things where it also makes sense to implement a bind operation. As you can see, either is there. And MetaMonad provides bind operations for all these things, and you can use these as well. And if you look at the documentation, there are the details what you can do with these things. So there is a documentation of the entire library and the tutorial as well. So as a summary, here is a list of features I've shown you that are inspired by the Haskell language and makes template metaprogramming easier. Yes? This? So the question is why there is no continuation. My answer is that I couldn't find a use case for it in template metaprogramming. Yes?
About exception, what was the use case you found for that?
So the question was, what was the use case for the exception thing? And it was about combining meta functions and doing error checking. So if you really want to do error checking, because you want to avoid errors coming from the bottom of your library, for example, if you build a DSL parser using metaparse I presented last year, and you've got a really complex template metaprogramming code, and at the bottom of it, there is an error in the DSL snippet, and you want to present it to the user, you don't want a deep template metaprogramming stack. You want to propagate that out and provide a meaningful error message.
Okay, so it's really, it's
Yes.
Well, couldn't the user like send that as an argument to the metaprogrammer?
So it can be asynchronous, yeah.
And that can be checked before calling less, or it can be just given less and check the results. So there are multiple ways. Of course, if you have this less and this min, you can just give it to min and report any error if there are problems. But I did not want to build an entire DSL parser to do a presentation. Are there other questions? Okay. So finally, I would like to show you how fact can be implemented using Boost MPL as it is now. As you can see, there is a helper meta function that had to be used due to the lack of laziness. But if you use things I have presented so far, you can implement fact this way, which is much more compact. And here is where you find the documentation of the library. You can find the source code on GitHub. So if you want to take advantage of any of these features, you can just go there and try it out. There is also a detailed tutorial on this website with all the features that the library provides. Yes? Okay, so the meta part comes from template metaprogramming. The monad thing comes from the monads of Haskell. So the question was, why metamonad? And the monad comes from the monads of Haskell. That's one use case of it. I have presented how it provides monads, but I intentionally did not call it monad just to avoid making people scared. I'm sorry? I knew the first part of it, and that inspired me of not calling these things monads. I didn't know this warm fuzzy thing. Are there other questions? Yes?
Does it depend on Boost MPL, or can it be used on its own?
The question was if it depends on Boost MPL, and the answer is yes. It uses Boost MPL in the background. Are there other questions? In that case, thank you for your attention.